evaluate the integral. So we have this region where x, this is inside x equals 2y to 2 and y from 0 to 1. If we write this region D, let's say D, this will be all x, y such that x is in between 2y to 2, 2y, x is in between 2y to 2, and y is in between 0 to 1. Okay, and we need to do this integration first, then we go for y. But here's a problem. So this antiderivative of ex squared with respect to x is almost impossible. We can still do this but using infinite series, and that's not the scope here, so we cannot do it. But how about if we are able to switch x and y? I meant if we have this situation here dy, and this will be the easiest thing to do because this ex squared behaves like a constant with respect to y. So you can just think like number 10, something like that, 10, and we know 10 y dy is just 10y. Okay, so we will switch the order of x and y, then our life will be easier. Okay, let's do that. Let me draw this region. Okay, so this region is, in fact, if we draw here, y goes from 0 to 1, so y equals 0, that's the x-axis, and y equals 1 horizontal line, and x is 2y, so we can write in this way, x equals 2y and x equals 2. So x equals 2 is just here, 2, so x equals 2, but x equals 2y, I mean this is same as y equals x over 2, then we can graph easily. If we take 0, we get 0, so it passes through the origin, and if we take 2, x equals 2, so y will be 1, so here. So this is the line x equals 2y or y equals x over 2. Then this region D is in fact this, okay, bounded by all curves, and we are trying to integrate ex squared in this region, and now we can define this region as follows. This is same as, or D equals x y. Now if we look at closely here, we can say x going from 0 to 2, okay, x going from 0 to 2, it doesn't matter where you write, and y going from where. So y here, if we look at this, it's like type 1, y from 0 to y equals x over 2. So y is 0 to x over 2. Okay, that will be the case. So let me rewrite this definite integral, an iterated integral with swapping x and y. So this is same as, we write dy then dx. Now x goes from here is x 0 to 2, and y goes from, just look at this, here is y equals 0 and upper curve is y equals x over 2. So 0 to x over 2 of same curve ex squared. Now we want to do this inside first, then outside. Okay, so this is same as x equals 0 to 2, antiderivative of ex squared with respect to y, just like constant, so ex squared survives, times 1, we can think times 1, and antiderivative of 1 is just y, and we need to evaluate from y equals 0 to ax over 2, and we have dx. Ax equals 0 to 2. Inside replace y by upper limit minus y by lower limit. So upper limit ex squared times y is x over 2 minus lower limit ex squared times 0, just 0, so we don't have to write the lower limit dx. Now we need to integrate. This is a product, so maybe use substitution or could be integration by parts. E raised to x squared, if we think x squared as u, I'm just trying u sub, then its derivative is 2x. We can always manage the constant, so constant 2x, derivative is 2x, so don't worry about 2x, and there is x, so we can use u sub. Okay, so let's say this is u, its derivative is 2x, there is no 2x, but we can always multiply by 2, and to balance, to counter this, we need to divide by 2 as well. Okay, if we do this, then this integral is, for me, we can bring now 2 times 2, 4 outside. This is pretty much 4. We can pull outside 1 over 4. This is like e raised to u, and 2x dx is du. So when we have eu du, it's just eu. Okay, so using this, we can write this is equal to 2 to 4 1/4 outside. Eu du is just eu, ex squared, and we evaluate from 0 to 2. Upper limit minus lower limit, so 1/4 e raised to 2 square, e raised to 4 minus e raised to 0 square 0, e raised to 0 is 1. So this is e to the 4th, a decimal number, minus 1. Final